It is estimated that the Milky Way alone contains billions of potentially habitable planets, orbiting stars much older than our own Sun. Therefore, it is reasonable to guess that alien civilizations should exist, many of which could be far more advanced than humanity, or at least advanced enough that we should already have detected some evidence of their existence. Yet, the universe remains quiet. This silence is known as the Fermi paradox. However, many people think this paradox assumes that, given enough time, a civilization can spread beyond their star system. But could that be wrong? Humanity has already placed a person on the moon and sent probes to Venus, Mars, and even distant asteroids. It is very likely that we will soon master interplanetary travel. Yet, some scientists believe that venturing beyond our solar system may be impossible, and that the technological limits might be closer than we think. Let's take a closer look. Recently, Antonio Gelis Filho proposed a concept of a universal limit to technological advancement. This theory could provide a solution to the Fermi paradox, one that allows for the existence of alien civilizations while also explaining the great cosmic silence. It suggests that we may be nearing this technological ceiling ourselves. This may sound unlikely considering that our technology is advancing faster than ever. I mean, in just a single human lifetime, we went from the first flight to landing on the moon, and yet there are already signs of a possible plateau. Let's have a look at Einstein's theories of relativity, which redefined space and time as fluid rather than fixed. The profound revelation was that gravity isn't a force pulling objects together, but a curvature of space-time itself. Massive objects like the Sun bend the space around them, causing planets to follow this curve as if marbles were rolling along a stretched-out trampoline. Meanwhile, quantum mechanics, zooming in on the tiniest bits of reality, revealed that particles do not exist in a single, fixed location, but in a cloud of probabilities, choosing a state only when observed. Even more strangely, particles appeared to be linked instantaneously across vast distances. Yet, these groundbreaking discoveries were made over a century ago. Though science has continued to advance, breakthroughs of this magnitude have become increasingly rare, and they come at tremendous cost. The Large Hadron Collider at CERN, for example, is among the most expensive scientific tools ever built, costing around $4.75 billion to construct. It is the largest and most powerful particle accelerator in existence. Beyond initial construction costs, CERN has invested roughly $1 billion into the detectors used to observe particle collisions. The LHC's operational costs are significant as well, nearing $1 billion annually. Historically, energy costs alone have accounted for about 20% of CERN's budget, with peak operation consuming up to 200 megawatts of electricity, enough to power approximately 120,000 homes. And what has it achieved? The LHC did confirm the existence of the Higgs boson. It was an impressive discovery, but it was expected, and it didn't cause a shift in our understanding of the universe the way relativity or quantum mechanics once did. Another super expensive modern project is the ITER fusion project, aimed at demonstrating the feasibility of nuclear fusion as a large-scale, carbon-free energy source. Initially budgeted at $7 billion, its costs have since tripled, and current projections estimate a final budget exceeding $25 billion. It faces huge scientific and economic challenges with no guaranteed breakthrough in energy production. As we push scientific boundaries, each new step requires exponentially greater resources. At the same time, groundbreaking discoveries are increasingly rare. This is one of the first signs that scientific advancement may have a limit. Beyond technological limits, the universal limit hypothesis suggests another barrier: societal complexity. Joseph Tainter's theory of societal collapse suggests that societies reach a point where the benefits of added complexity start to decrease. When hunter-gatherers evolved into industrialized societies, complexity initially fueled growth, but at a certain point, maintaining infrastructure and logistics requires ever-increasing resources, resulting in diminishing returns. Societies may eventually face pressures that force a choice: continue investing in large-scale scientific projects or prioritize essential infrastructure for survival. This shift isn't always deliberate. As complexity peaks and resources become limited, societies could naturally turn inward, focusing on survival within their planetary systems. While this complexity barrier applies to a civilization as a whole, it may also exist inside science itself. Today, most scientists work within established paradigms, adding pieces to a puzzle rather than reimagining it. Individual scientists often dedicate entire careers to a single subfield, which can limit opportunities for broader, revolutionary insights. Modern science also demands interdisciplinary expertise that's challenging to achieve, so new insights frequently come from collaborative teams rather than individual visionaries, and these collaborations are becoming more and more complex. Thomas Kuhn's concept of normal science might explain this pattern, where researchers solve problems within existing frameworks until anomalies accumulate, leading to a crisis and, eventually, a paradigm shift. The problem is, individual scientists are solving increasingly specific problems, which requires more and more complex collaborations to work on a bigger picture. If the universal limit hypothesis holds, we might still detect alien life, though perhaps not through direct contact. Civilizations may leave one-way messages in their nearby environments, awaiting discovery by others. While this wouldn't allow interstellar communication, it would at least confirm their existence. Such messages could resemble our own Voyager probes, durable, simple devices set on one-way journeys. Similarly, they might be occasional, high-power broadcasts in all directions, packed with as much information as possible. If the universal limit is valid, then beyond explaining the Fermi paradox, it suggests that humanity might be nearing its own technological limit. To disprove this theory, we would need to detect an alien civilization that has expanded beyond its home star system, or achieve such expansion ourselves. Yet, after decades of searching, no sign of extraterrestrial life has appeared. While we dream of grand projects, like Dyson spheres or the colonization of other star systems, these ambitions may remain within the realm of science fiction.